What I'm going to talk about is some quite recent developments, which the original part which I'll mention will be based on our paper with Ben Har and Radu Roiban. And there is also ongoing work with Oleg Lunin and Radu Roiban. So before I'll get to deformations, let me quickly remind you that there are few examples, maximally symmetric examples in 10-dimensional, say, type 2B string theory, which are related to familiar limits of various D-brane configurations, which are based on quite remarkable spaces, which are products of AdS and sphere. And in all these cases, one has, in addition to bosonic isometries, also superisometries. And naturally, these are based on super corsets, dividing the corresponding bosonic supergroup by bosonic subgroups. So these examples, in a sense, are kind of models which one would like to solve as much as possible, and because they'll definitely teach us not only about AdS CFT context, but also how to solve string theories in general in curved spaces with Ramon fluxes. So as we just heard from Joe, integrability plays a key role in the study of strings in AdS5S5. And the next question one would like to ask whether we can actually solve some other models which has less supersymmetry. And integrability is actually quite rare among generic sigma models with curved target space. But there are a few examples which one can generate by starting with known integrable model, basically taking orbifolds or T-duality, and familiar examples be the deformation and various generalizations. So the focus of my talk will be on a recent paper which is made quite remarkable proposal for how to construct a deformation of AdS5S5 superstring action, classical superstring action, such that the symmetry, explicit local symmetry, kind of disappears global symmetry of this model, apart from Cartan directions, but instead one gets classical Q-deformed symmetry based on the same PSU2 superalgebra. But in addition, this sigma model actually has light cone S matrix, which plays key role in the solution of AdS5 superstring, which happens to be Q-deformed S matrix, which appeared in independent developments based on just trying to construct natural generalization of light cone S matrix for AdS5S5 strings. So this model is non-supersymmetric. The target space background is non-supersymmetric, but it should be exactly solvable, and it has a huge hidden symmetry, which is not visible in point-like limit, but it's present in string theory. And so our aim will be to study aiming to study this model. We also start with simpler models which are based on AdS2S2, AdS3S3, and consider various special limits. So that's the focus of our work. And just jumping ahead, I'll give you some hint of where I'm going to. So consider usual AdS2S2 metric, which is here in brackets, some of these two terms. But the deformation which we'll be talking about involves this parameter kappa, and essentially it gives conformal factors in front of these two factors. So this is a metric which is not conformally flat, no longer conformally flat. In type 2B context, it will not be supersymmetric. There will be no residual supersymmetries. But it happens to define an integrable model with a hidden quantum symmetry. And it can be embedded in type 2B theory with adding Ramon fluxes. So this model is not conformal, but one ends up with conformal model, which is integrable, presumably quantum integrable. And in fact, there should be a way to actually generate exact quantum string spectrum, just like Joe reviewed in the case of AdS5S5. So similar model exists for AdS3S3 and AdS5S5. So let me start from just reviewing what we know about the strings in AdS and SN. So here, as I mentioned, the key point is to start with supergroup, and it can be split into subalgebra, which defines the supercorset, fermionic parts, and the corset parts. So similar split for the current, J1, J3 are fermionic, J0 is what you gauge, and J2 is Corset. So the action, superstring action looks kind of simple. It's simple to write it down. So these are currents, G is a metric, G hat belongs to supergroup, and that's how it looks like. H is tension. This model is classically integrable, kappa symmetric, UV finite. It should have quantum integrability, and in fact, for AdS5S5, we were much aided by the fact that it's due to N=4 theory, where weakly coupled limit is understood. So a lot came out, a lot of intuition how to solve AdS5S5 string theory came from gauge theory side. So how we actually solve, how we can abstract the way to solve this theory. What one should do, one should fix, at least that's the way how this is done at the moment. We can fix a particular vacuum, namely BMN vacuum, where we have momentum along a circle of S1, fix an adapted gauge to that, the gauge which essentially called light cone gauge, but it need not be really light cone, it's just time equal tau, and you fix momentum along the circle of BMN, along the BMN circle. So then one looks at symmetry preserved in this, by this vacuum choice, and demands this symmetry, which is subgroup of the bigger regional symmetry, centrally extends it, and that helps to, due to some shortening condition, helps to determine dispersion relation exactly for elementary excitations, which on gauge side are magnons, but on string side, these are just dressed by, essentially by perturbative string loops, dressed excitations of elementary excitation near BMN vacuum. Or equivalent, related point of view is this is dispersion relation of giant magnon solitons, which one can think of in this model. So then, using symmetry considerations, one essentially fixes to particleless matrix, imposing, following the same logic as is used for in S matrix bootstrapped by the malogicals in a relativistic case. So here, S matrix dispersion relation is non-relativistic, but essentially many steps go the same way, though technically they're more complicated, but eventually one could even determine the phase, the dressing phase, and check it against perturbative S matrix. And the end product is S matrix. Exact S matrix is a function of string tension, or square root of lambda. And once one has this matrix, one can construct a symptotic beta ansatz, then thermodynamic beta ansatz, and determine or quantum spectral curve, which we'll hear about in the next talk, and that gives exact spectrum. So the recent progress, which was actually luckily reviewed a little bit in Gong Show talk by Alessandro Sfandrini, is to do the same steps for AdS3S3 times torus, where there is a complication of massless modes, and these groups essentially contributed to this development. So there is much progress in this direction, plus we can also add, we can consider AdS3S3 T4 supported by mixture of Ramon and NS flux. And then there's a new parameter B. Symmetry is exactly the same, but there is a new parameter which is essentially level of Berzumino, K, or I call it B. And then again, integrability applies. And what we have here is a kind of line of theories which we go from Ramon case to NS case, which has also solution based on usual CFT. So the very interesting question, which remains to be understood, how one can kind of relate to different methods of solution, one based on S matrix, TBA, and the one which is based on CFT method. So in this NS Ramon case, dispersion relation changes, but derivation of it follows similar steps based on symmetry. So then one can also look at finite gap equations, dressing phases, and that's much recent work on that, and check also against perturbation theory. So what I'm trying to say is that in this case, one again hopes to find similar TBA eventually, and that will give exact spectrum of this model. AdS2S2 T6 case, again, there is some work on that, and next week there will be a paper which repeats the same symmetry argument construction and presents the S matrix up to one phase with constraints on this dressing phase. So this is all very good, but what about less supersymmetry? And as I already mentioned, there is, what I'm going to discuss is this review, this deformation of AdS5S5, which was suggested by these authors, Deluc, Magro, and Vicedo, which has Q-deformed PSU2 symmetry. And its light cone matrix happens to be Q-deformed AdS5S matrix, which appeared even earlier in the context which I'm going to discuss shortly. So then there is also already a suggestion how to go from that S matrix to TBA. So this deformed example without supersymmetry should be also exactly solvable with exact string spectrum. But there are many open questions. So if you just look at type 2B background for this deformed theory, it looks singular. There's only U1 isometries. For example, there's no Lorentz symmetry, there's no conformal symmetry, but there is a huge hidden symmetry. So it's by no means clear whether there is any gauge theory interpretation. There's no boundary here. So what that all means is not clear. So from string side, that's a solvable string model, which is closely related to original AdS5S5, but it remains to understand what actually the lessons of this example. So the origins of this whole construction are kind of mixed. So one is certain deformation, integrable deformation of principal chiron model, which has simplest example just Horst S3, which has hidden classical symmetry, Q-deformed classical symmetry. But there was also parallel independent development, which was started with Bayezid Karateyev. They were thinking about R matrix of Hubbard model, Q-deformed R matrix of Hubbard model, but using that building block, one can construct Q deformation, just one parameter generalization of light cone S matrix of AdS5S5 string. And that S matrix is just one parameter generalization of essentially exact AdS5S5 light cone S matrix. It happens, surprisingly, to relate original undeformed AdS5S5 string S matrix to something else, some other theory, which is kind of generalized Saint-Gaudens type theory, which happens to be Pohlmeier reduced theory for AdS5S5 string. So that happens, so this S matrix interpolates between S matrix of superstring and S matrix of Pohlmeier reduced theory for a particular value of this deformation parameter, which happens to be root of unity for complex Q. Now, this deformation, which I'm going to talk about, will be for real Q, but the reason I'm bringing this up because essentially the same construction in principle applies for any Q. So the idea will be to understand what's the sigma model behind this S matrix for real Q, and that will be this deformed deformation which I mentioned earlier. So what is Pohlmeier reduction? I need to be very, very brief. So essentially, given a Corset model, one can look at classical equations. Corset or supercorset doesn't really matter. Classical equations and impose Virasoro conditions and solve Virasoro conditions in terms of currents. So at the level, at classical level, one can reformulate, say, string equations on a Corset in terms of some other theory, classically equivalent, with classically equivalent integrable structure, which is, looks like, essentially looks like gauge-Versumino model with potential. And in superstring context, there will be also fermions. And the model which appears is essentially some generalized sigma model with symmetric space, based on symmetric space with potential. And these models are integrable. In the superstring context, they're also ultraviolet finite. And there is a natural relativistic S matrix associated to them. And that's this matrix, which is the endpoint of interpolation for this Q, which I mentioned. So that's what I was just saying, that this is the Pohlmeier reduction for superstring. It involves gauge-Versumino model with fermions and potential, and has relativistic S matrix, which is endpoint of interpolation where H is taken to infinity. And I forgot to say what is K. There is a string action with tension H, and there is a classically equivalent theory, which is Pohlmeier reduction, which is generalized Saint-Gaudens model. But in front of that Pohlmeier reduction, Pohlmeier reduced action, you can put a constant. It's gauge-Versumino model, so you put K. So that's a different constant, unrelated to H, and at the quantum level, they need not be related. So there is a kind of different directions, H and K, and this interpolating S matrix contains both. So given this S matrix, one can also take Q any, not necessarily this complex one, but real. And that will be the S matrix which this deformation which I mentioned earlier will be related to. So I can just skip this. So this S matrix can be constructed again using symmetries. This interpolating S matrix constructed using symmetries. It has uniform symmetry. And its face is essentially Bajor-Tiden-Staudacher face generalized in a proper way with this Q deformation parameter entering, kind of generalizing gamma functions to their quantum analog. So another ingredient in all this story is this sigma model, how we construct deformations of sigma model. There are examples which will come up later, which were known, like squash sphere or what is called sausage model, deformation of S2, which are integrable. And there is Fateev model, it's two-parameter deformation of S3. So the more general examples were suggested by Klimchik. So he actually considered just group space. So if you look at PCM, principal chiral model, which is just square of currents, you can put here K, the matrix, which is 1 minus, very strange construction, but that it gives you integral model. So K is 1 minus kappa, deformation parameter R. R is a certain operator on the algebra, which depends also on the group element G, and it depends on constant matrix R. And this constant matrix R satisfies what's called modified classical Yang-Baxter equation. So this bizarre name, Yang-Baxter sigma model, somewhat misleading. It has to do just with the fact that there is, in this construction, there is a constant matrix R here, which satisfies this algebraic relation. And usually this R can be chosen just plus minus 1 on positive negative roots and 0 on cartons. And that gives some sigma model with some target space metric, which has symmetry broken to U1 cartons times G. And the remarkable thing is it has, this construction preserves integrability, and it has, on Poisson brackets, there is this quantum algebra realized, with Q being some simple exponent function of kappa. So same can be repeated for corsets, essentially putting extra projector, which is, for Corset model, you need projector to the Corset part of the full G. And that's how it works. So this P2 is projection, and the algebra of conserved currents, which generate this quantum deformed symmetry, essentially the important part of it is written here. So Q is essentially kappa over effective coefficient H rescaled by kappa. And this model has some metrics, some antisymmetric tensor, and simplest example is this deformed S2, which is just this sausage model of Fateev-Hanov-ism, a logic of integrability of which was actually proved recently by Lukyanov, classical integrability. So same construction for AdS5S5, that's what was done by these people, Dilduk, Magro, and Visedo very recently. One repeats this story just for this super corset. So this, instead of Green-Schwarz action, which has this form with K0, which is just combination of projectors to corset part and fermionic parts, one puts here extra kappa, and the projector is also modified by kappa. So details are not important, but this is very simple kind of structure. The difference is that now, in addition to dependence on currents, you have explicit dependence on supergroup element G. So choosing particular coordinates is actually quite non-trivial to work out what's the form of this action. But action is known. The question is which background corresponds to that action. And that question turns out to be non-trivial. So the action has integrability, I mentioned that. It also has kappa symmetry. That gives indication that that should be type 2B background behind this action. And one can check it's finite. It has this classical quantum symmetry, and which is the type 2B background. So how do we get, we're given an action, which is presumably type 2B action in some background. How we find this background, we compare to what we should expect. So fermions should have covariant derivative with various Ramon fluxes there. And this is undeformed AdS5S5 metric. So in this paper, Arutunov, Barsatov, Frolov, they managed to work out what's bosonic part of this action. And they found this metric which looks complicated. So this is undeformed AdS5S5 in these familiar coordinates. And what happens is that you get extra functions, which kappa-dependent factors in various places. And the SO 2,4 times SO6 symmetry is broken just to U1 times 6, to Cartans only. So this metric looks complicated. There's also B menu field. So instead of trying to sort out what happens here, what's the background here, we will look at simple examples. So that's our motivation. So the important point here is there is a curvature singularity at rho equal kappa minus 1. So the no longer boundary, which was present in AdS5S5. And there is non-trivial dilaton, there is non-trivial Ramond fluxes. And the question is how to determine them. In a sense, this is a very strange problem. So we're given a metric, we're given intersymmetric tensor. One needs to find, and dilaton solves this equation, which is non-trivial because it's linear for exponent minus 5 for inverse effective coupling, but on many variables. So if there are 6 independent variables which R, rho, and 2 angles, which enter here. So given one need to find Ramond fluxes which solve their equations and have prescribed stress tensor. I don't think this question was actually addressed that way in the context of supergravity before. So it's non-trivial questions. Really, given metric, find the fluxes which support it. In principle, you can extract these fluxes from the action. But given the action is kind of complicated, it's not so simple to do. But remarkably, the S matrix, Lycon S matrix behind this bosonic part reproduces this Q-deformed S matrix, which I mentioned earlier, for real Q. So despite this complicated kind of structure of the background, there is very simple structure behind it, this Q-deformed Lycon, there is Q-deformed symmetry and Lycon S matrix. So, and that raises many questions. So what happens with the singularity? What's the gauge theory dual? Is there any at all? Maybe this is some gauge theory in some non-trivial background, non-commutative along the 4 dimensions, etc. But by no means it's obvious. So we look at special limits, and we look at particular choices of kappa, and we look at simpler models which are AdS3, S3, AdS2, S2. So what are special limits? So one special limit is maximal deformation. So suppose we take kappa to infinity, and surprisingly, this model happens to be T-dual to double Wick rotation of AdS5S5. So in this maximal, at kappa equals 0, we just have AdS5S5. Taking kappa to infinity and doing some formal T-duality, you end up with the theta 5 H5, supported by imaginary 5-form flux. So what that means is not clear, but it suggests that there is bigger picture if you complexify PSU224 and or AdS5S5, and there is some map between different regions under T-duality. Somewhat similar to what happens in two-dimensional black hole, presumably. And there is another deformation, which is imaginary deformation. So if you take kappa to be I kappa, actually the singularity in the metric goes away, but there will be I's in the fluxes. So what that means is unclear. And but just taking kappa to infinity, to I, we find that the resulting deformed metric, deformed model, becomes exactly this Paul-Meier reduced model for AdS5S5, embedded in superstring context. How embedded, just like PP wave background, which in light cone gauge becomes this Paul-Meier reduced model. Similar to models which were discussed by Maoz and Maldacena in the context of how we can embed, say, sine Gordon into as a PP wave background. So I still have 2 minutes, 3 minutes. Let me quickly run through these simple models, which actually quite illustrate what is going on. So AdS2S2 case happens to be related to this Fatiev-Onofri's homological sausage model, which is essentially deformation of S2 and similar deformation of AdS2. And AdS3S3 is related to Fatiev deformation of SU2 and SL2 model. So let me quickly run through AdS2S2. So that's the super Corset. And here one can extract, well, it's embedded, AdS2S2T4 is embedded in type 2B string as a limit of 4 D3 branes at equal charges, near horizon limit gives you this metric, which is AdS2S2, supported by 5-form flux, which has 2-form part and times the form on the 6 torus. Essentially, it's just a solution of effective 4-dimensional theory, Maxwell with dilaton, which is Bertotti-Robinson metric, we say this F2, electric magnetic F2. How the claim is there is a generalization of that solution with extra parameter kappa with this metric, very simple, simply looking metric, just conformal factors in front of AdS2 and S2. So what is special about this metric? It actually appeared before, as I mentioned already, so this part, S2 part, in the context of this FOZ model, which answers the following question. Suppose you take two-dimensional, take S2, put conformal factor, and ask when this metric is preserved by randomization group flow, when Ricci tensor is actually proportional to derivative of the metric. And the answer is this is the metric. And then they argued this is quantum integral model, et cetera, but important point is that once we generalize this to AdS2 and times S2, we get this metric, and there is a curvature singularity because of this metric is singular, but this has curvature singularity at kappa equal rho. Now, what we found is that generalization of this Bertotti-Robinson background to this metric, it's a solution of, say, type 2b or just four-dimensional metric of that with Ramon C-scalar N2 form, which looks very simple. But what is interesting about this background is that it's no longer factorizes into AdS2 and S2 parts. So the metric was just a direct product, but dilaton is not direct product. There is this function which depends on rho and r. And that's exact background. And what we see in this background, that dilaton is also singular at rho equal r. And yes, I'm finishing. It's singular at rho 1 over kappa. But square root of g times exponent is regular. So maybe some kind of T-duality resolves the singularity just in a familiar example like this. Now, I need to drop this discussion of special limit. Again, there is a maximal deformation is related to de Sitter type times ds2 h2. And similar story goes for AdS3 S3, where one finds this Fatiev model, which again is a stable point of organization group flow. That's how it appeared. Here it's embedded in the string theory as yes, I'm going to conclusions then. Conclusions. Summary, yes. So important, out of all this story, what is most remarkable, I would say, is that here we have just kind of problem which we are not familiar with. We're given an action, but we don't quite know which background, in the case of AdS5, S5. And the background looks singular. There are many Ramon fluxes, but behind this is a very nice structure. And light cone S matrix is known, and that means essentially string spectrum can be determined. So that suggests that we should better understand something also on the dual gauge theory side, what this deformation actually means there, and if it actually makes sense on this other side. And I guess I need to stop here. Thank you.
Questions? Yes.
Is there some sort of a GKP limit of the formation of the integrable system? Is it possible to study the behavior in the presence of a lot of derivatives, in a sense?
GKP means what?
For the string.
Oh, in this background, yes. You can study classical solutions, but it's not. Oh, yeah, you can probably find. It looks complicated, but it's integrable. It's a classically integrable model, and GKP string is actually just it will be similar on that. So yeah, but it's not clear what it will tell you immediately.
Okay.
I'm not sure if I understood. You study AdSN cross SN strings, and you consider deformation, and then you say that these geometries can be embedded in AdSN cross SN cross T to the appropriate power. And is that also an integrable background classically? do you actually see that there is lax connection and there is integrability also when you include the flat directions and the massless fermions?
So yeah, the question is as follows. So what I was discussing is a particular super Corset action, which is in AdS2S2 case is four-dimensional, essentially four-dimensional background, four-dimensional theory, or in AdS3S3 is six-dimensional. But if you embed it in type 2B theory, there will be 10-dimensional model with an extra directions. And that, in principle, these extra directions may decouple, may not decouple. It depends on details, on kappa symmetry, etc. I would say I expect it's integral, but it should be integral. But in a priori, that's a question. Yes.
Any other questions? Anybody from the galleries? Oh, yes.
Groups have a rational Q-deformed version and elliptic version. Is there any hint of elliptic deformation in your story?
Presumably this model, which yeah, if we go back to this Young-Baxter sigma model, in principle, depending on the group, depending on the Corset, there may be other deformations, but that was not studied. I think, yeah, the claim is that this model is integrable as long as you have classical, this equation satisfied. So whatever solution you can have.
Thank you.
Okay. We can thank Arkady again for a lovely talk.